Hi everyone, in this video we're going to revise KC and KP using past paper questions. Now this past paper question pack is provided in the link in the description below, or you can email my Gmail which is below and I will send these to you for you to work through. And then you can use this video afterwards to mark them and explain any that you got stuck on. So this video is suitable for A2 second year A-level students who are at the end of a topic. So they've finished their classes on KC and KP, or you're revising for your final exams. So in this first one, it refers to an equilibrium 20.1. That was on a previous question. So I've included that key information at the top. This is the overall reaction. It's all in the gas phase, and we've got a delta H as well that's negative. Now this is a KP question, and this is the equilibrium constant for gases. And it says we've got some initial moles, so we mix together this many moles of the reactants and we allow the mixture to reach equilibrium. And it says 75% of this reactant has been converted to NO2, the product. So the first thing we want to do is work out 75% of this to find out how much has been converted into the product. And we can use what's called an ICE table or RICE. So R stands for reaction, which we have up here, I for initial moles, C for the change in moles, and E for the equilibrium moles, so the amounts left at equilibrium. And the first thing we do is we plug in the amounts from the question. So initially, that's I at the start of the reaction, we have 1.6 moles of nitric oxide, 1.5 moles of oxygen. And we always have 0 moles of the product because this is right at the start of the reaction. The reactants haven't had time to react yet, so 0 products. And we've worked out 75% of this, which gives us the amount of product remaining at equilibrium. So we've put in these 3 values so far, and this 0. Next, we can subtract 1.2 take 0, which is obviously 1.2, to get a change in moles for this product. And then we can use the ratios in the balanced equation to work out the changes in the other 2. And that's how we calculate the equilibrium moles for these. So this is a 2 to 2. The ratio is the same. That means the change will be the same. So I've put plus here because we're forming product, and minus here because reactant is getting used up. So the value is the same, 1.2, because the ratio is the same, but the sign's different. This is getting used up and this is forming. So we do this sum, this subtraction. 1.6 minus 1.2 gives 0.4. Then if we look at the ratio here, it's 2 to 1. That means the change in moles for oxygen will be half that of the things with a ratio of 2. So 1.2 divided by 2 gives 0.6 because the ratio is half. And we do 1.5 minus 0.6 because this is a reactant, it's getting used up, and we get 0.9. Now, since this is a KP question, we can't just plug these moles in to the expression. We need to use partial pressures. So the first thing we need to do is add up the total moles at equilibrium, these 3 moles at the bottom, and we get 2.5. And if you look here, I've shown where the marks are awarded as well. First mark for the equilibrium moles, second mark for working out the total moles at equilibrium. The next thing we need to do is work out the partial pressures of each of these things in the reaction, because that's what we're going to plug in to the KP expression. And the equation for that is partial pressure equals mole fraction times total pressure. And to get mole fraction, we do the moles, the equilibrium moles, of that particular thing in the reaction divided by the total moles that we worked out here. And then the overall pressure is here in the question, in megapascals. And then we plug our partial pressures into the Kp expression, raise to the power of the number of moles in the equation, and we get our Kp value. And it wants it to 3 significant figures, 20.6. Then part 2, it says, the chemist repeats the experiment 3 times. In each experiment, they make one change, but use the same initial amounts of the reactants. Complete the table to show the predicted effect of each change compared with the original. Use the words greater, smaller, or the same. So the first column is asking about the change in Kp, and we've got temperature, pressure, and catalyst. Pressure and catalyst that's naughty. Pressure and catalyst do not affect the Kp value, only temperature does. So if we look back at the delta H value, the reaction is exothermic in the forward direction. That means if we increase the temperature, the reaction will move to the left-hand side. If the reaction moves to the left-hand side, the Kp value will get smaller because it's moving towards the reactant. So that means Kp will be less than 1. And that's why it's smaller, same, same. So we need all 3 of those correct in that column for 1 mark. Then it's asking about equilibrium amount of NO2, that is the product. So if we increase the temperature, same reason, the reaction's moving to the left, so we'll get less product, more reactants. If we increase the pressure, we need to count the gas moles. We've got 3 gas moles on the left, 2 gas moles on the right. So increasing the pressure moves the reaction to the side with the fewer gas moles, which is the product side. So that will increase the amount of the product for this reaction. And the catalyst, that doesn't affect the amount of product. We just reach the equilibrium position faster. Then temperature increase, that will increase the rate. Pressure increase the rate, and so does catalyst as well. Next, we've got a multiple choice question. And it gives us the equilibrium moles of 3 things in a reaction and a total pressure. And it's asking us for the partial pressure of one of these, the product. So to do that, the first thing we need to do is work out the total moles. So we add the moles together, and then we can work out the mole fraction. So to get the mole fraction, we do the moles of the SO3, because that's what the question's asking for, over the total moles of everything in that reaction. And we get 0.1. Now we can work out partial pressure doing mole fraction times the overall pressure, which is here in the question. And we get 25 atmospheres. So the unit of partial pressure is going to be the same as the total pressure, and it's whatever it gives you in the question. This next one is about Kc. So it gives us a mass of methanol and a mass of ethanoic acid. I've written the reaction here. This is a part B, so maybe obviously I've chopped off that bit of the question, but it's here anyway. And then it says calculate Kc. So since we're given masses, we're going to use the equation mass over mR to get the moles. After we've got the moles of each of these 2 things, we're going to use a Rice table. So reaction, initial moles, change, and equilibrium moles. We've put in the things we have already, so we've worked out our initial moles here of the 2 reactants. The products, it will always be 0 right at the start of the reaction. So initially, we've got 0 products. And then here in the question, it gives us an equilibrium mole value for the acid, so we plug that in here. And this is where we're going to start then. So we can do a subtraction, 0.2 minus 0.03, and that will give us a change. Next, we can look at the ratios in the balanced equation, which happens to be 1 to 1 to 1 to 1 of everything. So that means the change is 0.17 for everything. And remember, the change is minus for reactants because they're being used up, and positive for products because they're being produced. So then for the methanol, we do this sum, the initial moles minus the change, give the equilibrium moles. And for the products, we start with 0, we add the change on, and we get the equilibrium moles formed. Then for Kc, we use these equilibrium moles, plug them into the Kc expression, and we get 7.4. Next question is question 13. It says we've got a mixture of two gases and a total pressure of 1.42 atmospheres. And we've got a mole fraction of the nitrogen. And it's asking for the partial pressure of oxygen. The first thing we do, we need to know that mole fractions always add to 1 because they're fractions. So that means we can do 1 minus the mole fraction of the nitrogen to get the mole fraction of the oxygen, which is 0.3. Now we can work out the partial pressure of the oxygen by doing mole fraction of oxygen times the overall pressure, which is there. And we get 0.426, which is B. In this question, it's asking for a Kp expression for the reaction above and the units of Kp as well. So Kp equals the partial pressures, and we use curved brackets for this. Unlike Kc, where we use square brackets because square brackets mean concentration, but here they're partial pressures. So anyway, it's products raised to the power of their number of moles over reactants times together, raised to their number of moles. Then for the units of pressure here are atmospheres, so same as the total pressure. And we raise that to the number of moles, so if it's squared here, then we square those units. And what we do is, after plugging in the units into the expression, we cancel out on top and bottom anything that's the same. If there's anything left over on the bottom, we move it to the top. And at the moment, when that's on the bottom, that's atmospheres to the power +1. We just don't show the 1. When we move it to the top, it changes signs, so it becomes atmospheres -1. So they're the units of Kp for this one. Then for the next part of the question, it's asking us to calculate Kp. So there's quite a lot of information here. If we see what we've got, we can underline anything important. So we've got a volume for a gas and it's at room temperature and pressure. That means we need to use the molar volume equation. So any gas at room temperature and pressure occupies 24 decimeters cubed, and we can use this equation to work out moles when we've got volume. So to get moles of the SO2, we do the volume over 24 and it gives us this amount of moles. Then we're given oxygen in grams, so we've got a mass of oxygen and we can work out moles of that doing mass over mR. And make sure you use 32 for oxygen because it's diatomic. So it's O2, 2 times 16. Next we can use a rice or an ice table again. So R for reaction, I for initial moles, C for change, E for equilibrium moles. Pop in those moles we've just worked out for the oxygen and the SO2. There they are. 0 for the product because it's right at the start of the reaction. We're given a value for equilibrium moles of the product, so we can plug that in. Then from that we can work out a change. This minus this gives that. And then we use the ratios to work out the changes for the other two. And from that we can work out the equilibrium moles of those as well. And since it's a Kp question, after we've got the equilibrium moles, we need to add them together to get the total moles. Then we can work out partial pressures because that's what we're plugging in to the Kp expression. So that will be mole fraction times overall pressure. Plug those values in, the partial pressures, raise them to the values, raise them to the number of moles that are in the balanced equation, and it asks us for 3 significant figures in our answer, 27.2. This next one is a Kc question, and it's asking for the Kc expression and units for the reaction above. So we do products over reactants raised to the power of a number of moles. Since it's Kc, to get the units, we plug in units of concentration into the same expression. raised to the powers of the number of moles. Cancel out anything that's the same on top and bottom. Anything that's on the bottom, move it to the top, and that will change its signs. So it was moles plus 1, dm minus 3, and now it becomes moles minus 1, dm plus 3. This next one, the chemist mixes together nitrogen and oxygen. So it's a different reaction. And pressurizes the gases so their total volume is 4. That's important, we'll have to do something with that. The mixture is allowed to reach equilibrium, constant temperature and volume. We've got moles present at equilibrium and we've got a value of Kc. So we're going to have to rearrange to find an equilibrium amount. First thing we need to do then, since the total volume isn't 1 decimeters cubed, we need to divide our moles, which we're given here in the question, by 4. So moles over volume gives us the concentration. Now we've got the concentrations, we can plug those into the Kc expression. We do have Kc, it's 45, so we can call the thing we're trying to work out X. And we're going to rearrange for that. So I've plugged in the numbers that I've got, rearrange for X. We need to get rid of the squared as well. So that's come from there being 2 moles of it. The ratio is 2 in that overall equation. So to get rid of a squared, we need to square root both sides. And then the final answer, it wants us to give it in moles. So to convert the value back to moles, we do concentration times volume. So the concentration we've worked out from the Kc expression times that same overall volume again, and we get 1.2. In this question, we've got some data about temperatures and Kp values, and it says predict with a reason whether the forward reaction is exothermic or endothermic. So we're not given a delta H, we have to figure it out from this data here. So I've just had a look and written down what I've seen, and I've said as temperature increases, Kp decreases. That means if Kp decreases, the position of equilibrium is moving towards the reactants. So if we're increasing temperature and the equilibrium moves towards the reactants, that must mean that the forward reaction is exothermic. The next question is more descriptive. It says the chemist increases the pressure of the equilibrium mixture at the same temperature. State and explain in terms of Kp how you'd expect the equilibrium position to change. So we need to talk about how the pressure will affect Kp, but it wants us to talk about how Kp works, like as a ratio. So the first mark, increase in the pressure, this is Le Chatelier's principle, shifts the position of equilibrium to the side with the fewest gas moles, which in this case is the right, because we've got 3 to 2. Now changing the pressure does not change the value of Kp, since the ratio adjusts to restore Kp, and the increased pressure would initially cause Kp to decrease before it is restored. Question 20 is about Le Chatelier's principle. We've got an equation. It says it's a way of making hydrogen gas in industry. Explain the conditions of temperature and pressure for a maximum yield of hydrogen and why the actual conditions used may be different. So we need to look at the amount of gas moles on both sides. We've got 2 on the left, 4 on the right. We've got a delta H that's positive. That means the forward reaction is endothermic. So for a good yield of product, a good yield of hydrogen, a high temperature and a low pressure are needed. That's what will shift the reaction to the right-hand side. Then we need some explanation. This is because the forward reaction is endothermic. That's our second mark. And there's a greater number of gas moles on the right. That is the third mark. Now, why might the actual conditions be different? That's because a low pressure, even though that shifts the reaction towards the product that we want, it means we get a quite slower rate of reaction. Whereas a high temperature, that's quite costly in terms of energy as well. So this next question, we've got our reaction here. We've got a total volume of 400 centimeters cubed, and we've got equilibrium moles of these two reactants. But the first question just wants us to write the Kc expression and get the units. So same as before, products over reactants, plug in your units, cancel anything out that's the same, anything on the bottom, move it to the top, and it will change its signs. Oh, +3. Part 2 then is the calculation. Determine the amount in moles of SO3, and we're given a Kc value. That means we have to rearrange in terms of the thing we want to find out, the SO3. And the question wants the answer in moles. So since we've got a Kc value, we have to initially convert our moles into concentrations, then convert them back again to moles for the final answer, because we've got that Kc value with units of concentration. So to get concentrations, we do moles over total volume. After we've got our concentrations, we can plug them into the expression and rearrange in terms of the SO3 which we want to find. We need to remove this squared. To do that, we're going to square root both sides, and then we just plug our numbers in. That's the Kc, that's the SO2, raised to the number of moles, because there's two lots in the balanced equation, and that is the oxygen. And we get 6.12. That's a concentration in moles per decimeter cubed. We need to convert that back to moles now, because that's what the answer wants. So to do that, we do concentration times the overall volume. So 400 centimeters cubed was the volume, but we need that in decimeters cubed, so the units are consistent, and we get 2.45.